Hi, I'm Steve. You can call me Steve. Over the past few videos, I've shown a bewildering array of chemical structures with very little explanation, and left them on screen for about 3.5 seconds before cutting away to talk about them while you can't see them. I also threw up a bunch of chemical names which probably looked like a collection of nonsense syllables. I didn't have time in those videos to go into more detail about what all those syllables mean, so I'll do it now. While they do look daunting, chemical names are reasonably straightforward. They're a code that describes what the molecule looks like. And once you understand the code, you can understand the molecule. The modern system is named after 3 organic chemists who developed it: Kahn, Ingold, and Prelog. Just as a side note, I've gone water skiing with Ingold's son, who is also an award-winning chemist. Okay, enough time wasting. Let's just dive in. This is the anti-knock agent added to gasoline, commonly referred to as octane. Each intersection of the lines represents a carbon atom, and the lines themselves represent bonds between atoms. Every carbon atom must have 4 bonds, so any intersection that doesn't have 4 lines coming off it has the rest of its bond filled by hydrogen atoms, which this method of drawing molecules doesn't always show. I chose a molecule containing only hydrogen and carbon, called a hydrocarbon, because it's the simplest starting point. The official name of this molecule is 2,2,4-trimethylpentane, which is a bit of a mouthful. To explain what this means, I'm going to start at the end of the word. The suffix "ane" in chemistry means that the molecule contains only carbon-carbon single bonds. All of the bonds between carbons are single lines, not double or triple. When naming organic molecules, the first thing you have to do is find the longest chain of carbon atoms. Here, I've drawn the molecule such that the long chain is 5 atoms more or less straight across the screen. I've done this for clarity, but it's not uncommon for teachers to put questions on tests where a very long side branch will contain a longer chain than the ones across the page. In this example, if you start at one of the carbons sticking off the side, you'll find that no matter how you try to trace a path, you never get one longer than 5. Once we've counted how long the chain is, we assign it the name associated with that number. For 5, that's pent, so we have pentane. For chains of 5 or more, the name corresponds to the appropriate Greek number: penta, hexa, hepta, octa, whatever. For 4 and below, it's an arbitrary non-word derived from some historical association with the first identified molecule containing that many carbons. Now that we have the main chain named, it's time to name the sticky off bits, called substituents. We have 3 substituents, all of them consisting of a single carbon. The name associated with a 1-carbon section is meth, and yes, that's where the meth in crystal meth comes from. Things that are substituents get an "il" added to their name, so it's a methyl. When there's more than one of the same substituent, there's a prefix to indicate that number, in this case tri. Finally, you have to give the address of each substituent. You have to indicate which carbon of the main chain they all live on. Start at the left end of the chain and number each carbon sequentially 1 through 5. 2 methyls live on carbon 2, and 1 lives on 4. Those numbers go at the front of the chemical name, separated from the words by a dash. 2,2,4-trimethylpentane. One important thing to consider is that you can start numbering the chain from either end. If we start on the right side, the addresses become 4, 4, and 2. The rule here is to pick the end that gives the smallest numbers to the most substituents. 2 2s and a 4 are smaller than 2 4s and a 2, so the original numbering scheme was correct. That's the general idea behind chemical names, a description of the structure. The more complicated the structure, the more complicated the name. Because it's a set of rules, we just need to learn the rules to name any chemical, rather than memorizing millions of different names. Describing all of those rules generally occupies the first chapter of many organic chemistry textbooks, but once you get the hang of them, they're reasonably intuitive. I've just brushed the surface here. There's also an older naming scheme that's still hanging on in backward parts of the world like the US. And a lot of very common ring-shaped structures have their own unique name because it's hard to name a chain that's a circle. Still, once you get the hang of it, it's not that scary. Thanks for watching. I've been Steve.